All right, so what we're doing today is basically understanding the non-trivial action from C3 to C2 squared and how to induce the action, right? So we feeling a little rusty, but we basically worked on these in the last session. We just kind of finally understood the concept of the action from C3 to C2 squared, right? And the fact that, and I might come back to these, right? But the fact that it's like the action from group to group is actually a mapping from the starting group, so C3, to the automorphisms of the target group. And then the way you build the operation of the Cartesian Cartesian product group is by applying that automorphism that you've selected to the first element. Yeah, exactly. When you're doing the multiplication. What's important to know, right? Because again, we've got tools and systems, right? So it's important to understand what this means. And I think that is essentially what's happening here is nothing else than, in an abstract way, you've got a group, you've got two groups. Those groups represent kind of the way that I understand these, right? So they represent, I don't know if it's the right way to put it, like an algebra. Let's ask Grok. So can I delete this stuff? I don't know if I should keep those conversations, to be honest. Probably yes, because it's part of the group, right? Part of the project. Maybe I'll end up doing a project per problem. But yeah, so what's the definition of an algebra in the context of group theory? Is a group an algebra of vector space over a field? Okay, a ring. Okay, and how does an algebra relate to a group? So connections through structures like group algebras. Okay, it's fine. Let's not get into these rabbit holes. So this is nothing to do. So the algebra is something else. It's somehow similar, right? Because it's basically combines the properties of vector space and a field, whatever that is. Although we have fields in the question here, right? So it's a large field with characteristic 2. How many blocks does KG have? So I guess it's going to do some. I guess you maybe can define a field from a group. That's going to be the next thing. But anyway, so we've got, okay, so let's try to summarize these. Or give me a brief description of the non-trivial action from C3 to C2 squared, and define the operation, or define basically yeah, okay, so this action, and define the define the semi-direct product, or the semi-product C of C2 squared R times C3 with that only non-trivial action. Keep the answer short. So the non-trivial action of C3 is an automorphism where the generator of C3 acts on C2 by permuting its non-identity elements cyclically. So it's just a permutation. The semi-direct product with this action is a group of order 12 isomorphic to the alternating group A4. Okay, isomorphic to the alternating group A4 where C3 acts non-trivially on the normal subgroup C2 square. Okay, wait. Okay, that's one step. Because we have the semi-direct product with this action. Let's construct the semi-direct product. Again, it's not all we exactly need because it's not going to be C3. So what we're going to need is these, right? So maybe let's just jump to that. So let's use SymPy to define the group. So to define the group, to define this group, so then the group S defined as this, and the group D defined as C2 squared, and use SymPy to define the semi-product. The semi-product SR times D, and use an action induced by the action you mentioned above. That's gonna be, let's see what happens, okay? Be a bit verbose this time. And notice that it's actually, oh no, now it's actually using grok 4 because it's asking me to go through the quick answer, so it's actually really thinking a little more. Order 108. Okay, that's gonna be a little tricky, right? That is order 27, right? Remember, we've done these here to make it easier, so to define the action, to understand the action. And now I literally want to calculate these using that action, but let's see. It just doesn't seem like it's too easy to use SymPy for that, because to be honest, it's like using SymPy anyway to define it in terms of rules and whatnot, like in the previous conversations. Can I see the whole thinking going on? Yeah, I think so. So it's the previous actions context. Was C3 on C2 square, which is faithful, suggesting similar approach for C3 on C. What is it doing? I think it's getting confused. I think it's getting confused. Extra special properties. I think it's... Why has it thought so much about all this stuff? I mean, let's see, extra special properties, whatever that is, for the action of the extra special group. Okay, extra special meaning the three, like that's a thing, the way that's the name of this group. Or the type, right? D acts on the quotient C3 I have to define S and SymPy using the F group feature. I can explain it. No, this is already telling me that it's not. It's just getting lost in the way that I've asked it. Maybe, maybe. The map is in order. No, I'm gonna ask it to stop. I don't follow, so I don't think it's going down the right path. Maybe it is, right? So maybe it is, but it doesn't really help me. So I'm going to do this. Let's define this first. Let's define this in SymPy. Define this in SymPy. Give me a code file to work with. It's a permutation group representation. Why is it defining D now? And why is it defining the actions? That's not like it's not what I ask it to do. But I guess it's trying to infer too much. It's trying to infer too much of what it has as context, because it's probably using all these conversations as context. And to be honest, I don't know if that's what I want. So what if I'm just gonna create one outside of this project, okay? I'm gonna ask it the same. So construct this in SymPy. Construct the following group theory in SymPy. And let's study this well, because let's study this group well, because we haven't done that. So we've spent time. Okay, generate the group elements. Can I run this code? Verification. Let's run this code. Okay, it's actually breaking. Error. Let's fix it. Because essentially it's dr times s what we're calculating, right? So let's just do that construction. Now we know what it means with the action and all this kind of stuff. So let me see. Yeah, it takes time to ramp up. I think, yeah, that's. I'm not so sure that was smart to use the project here, because I mean, yeah, it does kind of use everything. It doesn't seem like I'm benefiting from the project concept too much here, because as I built up what I built up, like the information that I'm building up, it's just helping me. It's not supposed to help the LLM. The LLM is kind of supposed to know that already, right? So let's run did it fix it, or should print all the 27 elements, right? No. Can you open the code editor? No, I meant here. I just kind of wanted to. Well, let's see if it's fixed it. Yeah, okay. So actually it's printed 27 elements, which are basically matrices. Let's try to understand that, okay? Yeah, I think, I mean, what's more, I think we're gonna have to, can I just move that to project HLE streams? Yes. But I don't know if that's a good idea, but it's maybe there's a way that I can run a chat inside a project. It helps me group stuff, but it's like I don't want to, I sometimes I just wanted to ignore the context of the other conversations. And now I just need to study that, okay? I'm not going to do this now because I've already, how much time do I have? 10 more minutes. Come on, let's do that. There's a lot to unpack here. There's a lot to unpack here. So to construct a group in SymPy, we need to interpret the group notation and use SymPy's group theory capabilities. Arising the concept of finite groups, particularly in group theory related to P groups, groups of line type, whatever that is. The first is specific 3 group, a group of order, a power of 3 with a structure described by the exponent 1 plus 2. Often indicates a specific type as the group as the plus type. And special groups, the groups focus on the most common interpretation of group theory. So an extra special P group of order 1 plus 2 order 3. Okay, so this means okay, whatever, I don't know, that's just the way they calculate the order for these groups. 2 isomorphism classes for odd primes, one with exponent P and one with exponent P2. With exponent P2, one of exponent P, often denoted these one exponent P2. Okay, the plus suggests the expression group is exponent 3. That hasn't really told me a lot. So the expression is center of order 3. Center of order 3 isomorphic 2. I forgot what that 1 plus 2 meant, but it had to do with the structure of whatever the center of the group was. I almost feel like I could have a split screen, you know, where I just, because sometimes I'm like, I'm struggling to come back to a concept. I say like, what was the center of a group? And I don't want to break that thread in here. So I probably want to have that other conversation as well. Easy to access. But I'll try that next time. Oh. Z is central and okay, so it's just generating the elements, group elements, boom, generate group X, Y, Z. So these are the generators, and then that basically gives me the list of elements. These ones here. It's a group. And now essentially we're saying that we want to have that times C, so the product of C2 squared and these with the action where there's a permutation of C2 squared, because that's what it means for the action to be induced by that. let's sorry, I have to go back to understanding that group. I have to come back to understanding that group. A group of order a power of 3 with a structure described by the exponent 1 plus 2. So that describes the structure. The plus, we'll think about it later. Understand the group. The extra special group has order 27, center of order 3, isomorphic to... Let's go back to what the center of... What's the center of a group? Let's go back to what's the center? Ignore other combos. What's the center of a group? Yeah, okay, so it's the set of elements in G that commute with every element of the group. Oh, okay, that's the center. Okay, so this means that's what would be helpful to kind of come back to these. So so okay, so a specific 3 group, a group of order of power 3, a 3 group. The subscript plus indicates a specific. So, but what was the P group? What was the P group again? What was a P group? You kind of kind of really refresh all that, right? So the set of a non-trivial finite P group is non-trivial. Pardon. Yeah, but what is a P group? It's a group in which every element has order that is a power of a fixed prime number. Okay. So, okay, so that defines a rule. So, okay, so a P group. So a P group is a group in which every element has an order that is a power of a fixed prime number, P. And so because we have a 3 group, this means that every element in this group has an order that is a power of 3. Let's try to construct this step by step, because it's too many rules at once. Give me a construction of a P group with P equals 3 in SymPy. Go straight to answering my question. Give me code. And I think I'll stop here. Again, what we're doing is this. So we're now so we've kind of understood all that. We've understood what each of these elements is. We understood the R product. We've understood in the past like 8-9 videos, right? What the action of S on D means. We've understood that, calculated the action, the only non-trivial action from C3 to C2 squared. So now we understand what this means, and now we're kind of really tackling the problem again from scratch. So essentially we need to build S. So we need to understand how to build S, and then we need to actually build the product of D R times S. That's what we're going to be doing in the next videos, okay? So define the prime P equals 3 in order 1. Okay, so it's a group in which every element has order that is a part of a fixed prime number. Equivalently, a P group is a group whose order is a part of P. Finite P group. So G is a finite group. It is a P group if its order of Pn is something P. The P group, there's many things that can be a P group. I guess that's the point, right? So construct a non-abelian 3 group of order 9. 2 permutations that satisfy the relations of the Eisenberg group. A permutation, B permutation. What? The commutator generates the center. What? What? Of the 3 group of order 9. Okay. But that makes no sense, right? There should be... So... So a finite P group... Okay, so... If I keep saying okay, so... A P group is a group in which every element has order that is a power of a fixed prime number P. Equivalently, a P group is a group whose order is a power of P for some non-negative n. So, but then that's wrong, right? Because it says there's 8 elements, and 8 there's no power of So, if G is a finite group, it is a P group if its order is P to the power of n for some prime P and integer n. A group of order 8 is a 2 group. Exactly. A group of order 8 is a 2 group. Okay. Define the prime P equals 3 and order P squared 9. Infinite P groups. In the infinite case, a group is a P group if every element has order pk for some k. An example of a perfect group, whatever, yeah. I saw properties of these. The center of a non-trivial finite P group is non-trivial. Every P group is a nilpotent, meaning it has a central series where the factors are abelian. P groups have subgroups of all possible orders. Okay, so the properties I'm not really interested in. Okay, P group. It's fine. So a P group is okay. So now, what? Explain me the code you've generated. And why are you using permutations? That's generators. So the code constructs a non-abelian P group for P3 and order 9 specific Heisenberg group. There's an explanation. Okay, the prime order. The generators 2 permutations A and B are defined, each of order 3. Order 3 permutation. to 0. But what does this mean? What is this? So, what does this notation mean in SymPy? I think I'm going to leave it here, because that's what I need to understand, how it's using notation permutation. Defines a permutation in cycle notation, representing a specific way to rearrange a set of elements. Let's break it down. So permutation is bijection from a set of itself, often represented as a rearrangement of a finite set of elements. In cycle notation, a permutation is written as a product of disjoint cycles. Each cycle ABC indicates that the element A maps to B, B to C, and C to A. Okay, 0 to 1, 1 to 2, and 2 to 0. Okay, so that's, okay, it's a permutation. Okay, it's a permutation of 8 elements, basically. It's one specific mapping. Okay, and then essentially what, and why is this order 3? Because if we apply this permutation 3 times, you're gonna get the same set. Can you show me with an example that if I apply this permutation 3 times, I get back to the what do I get back? Order 3. I get back the identity. Yeah, exactly. That's what it means, right? Three disjoint cycles. 1 goes to 0 goes to 1 goes to 2, 2 goes to 0. Yeah, true. Okay. Just a list count multiple of the cycle length, which is 3. Yeah, okay. The identity. Yeah, exactly. Let's run this. Using code to prove this stuff is what makes the most sense. False. No, but it's fine because it's like 0, 1, 2, 3, 4. That's the point. It's not about the identity. It's about the fact that if you apply it 3 times, you're back to its. You're back to the beginning, which is the same as applying the identity, which means no permutation, right? The initial is 0, 1, 2. So please P1. P equals P 0, 1, 2, 3, 4, 5, 6, 7. Yeah, and then you apply these 3 times. All right, so now we're defining a group P3, which is basically a group where each generator, that's the definition of the group, where each element is of order 3 or a power of 3. And that's a group of order 9. Partition group AB. A, B, B, A. Okay, I have to stop, but I think I'm getting somewhere. So we're, and then I'm gonna add more constraints on top of that. I'm gonna try to say, cool, now let's construct like the P, so P group with P equals 3, but like 1 plus 2. What does this mean, right? So how does this restrict the kind of constructions that we can make for this group? Cool. See you in the next session.